Modern manufacturing looks flawless. Metal is cut with micron precision. Machines move at 20,000 revolutions per minute. Robotic arms weld, mill, and assemble with movements so exact they seem almost artificial. On camera, a 5-axis CNC machine carving aerospace aluminum looks like the definition of perfection. Clean chips, mirror-like surfaces, absolute control. It feels like we've mastered physics. But precision at small scale is not the same as stability at large scale. And when modern manufacturing fails, it rarely fails with sparks and explosions. It fails quietly, mathematically, and at scale. A single CNC part can be machined perfectly. The simulation runs clean. The CAM system shows no collision. The tolerance window of ±0.01 mm is achieved. Surface roughness meets specification. Quality control signs off the first piece. Everything is correct, but production is not about one part. It is about 10,000, 50,000, around the clock, 3 shifts, continuous load. That's where the difference between precision and stability becomes visible. In aerospace manufacturing, tolerances are extreme. Companies like Boeing and Airbus operate in dimensional ranges where tiny deviations propagate across meters of structure. During major aircraft programs, structural components were produced that individually met machining specifications. Each bracket, rib, or frame section passed inspection on its own. But during final assembly, components did not align as expected. Small geometric variations accumulated across large assemblies. Tolerance chains stacked. Fastener holes required rework. Structural sections required adjustment. What looked like acceptable variation in isolation became critical misalignment in combination. The parts were not wrong. The system was unstable. The same pattern appears outside aerospace. Manufacturing always starts controlled. A process is optimized. Feeds and speeds are tuned. Tool paths are refined. The first batch runs smoothly, then production scales. Spindle speeds increase to reduce cycle time. Radial engagement is optimized to remove more material per pass. Machines run 24 hours a day. Heat builds inside the spindle cartridge. Bearings operate under continuous high-frequency load. Tool holders experience thousands of micro-impacts per minute. Physics does not negotiate. A small increase in radial engagement does not create a small increase in cutting force. Cutting force scales non-linearly with chip thickness and contact area. Slight tool deflection changes effective engagement. That changes load. That changes vibration behavior. Regenerative chatter can emerge from conditions that were stable just days earlier. Heat introduces another layer. Steel structures expand. Linear guides shift by microns. Thermal drift accumulates during long shifts. A machine calibrated in the morning may behave differently at midnight. Individually, each deviation is tiny. Collectively, they alter geometry. Surface finish begins to fluctuate. Tool life shortens by 5%. Scrap rate increases by 3%. Cycle time stretches slightly as operators compensate by reducing feed rates. Nothing dramatic. No crash, no emergency stop. Just gradual erosion of precision. During the rapid production ramp of electric vehicles, Tesla experienced what became widely known as production hell. The issue was not simply broken machines. It was system behavior under scale. High levels of automation worked in theory, but real production introduced variability in materials, alignment, tolerance stacking, and human interaction. Over-automation removed flexibility. Bottlenecks emerged where processes could not adapt quickly enough. The lesson was not that automation fails. The lesson was that complex systems behave differently at scale than they do in controlled trials. Inside every high-speed CNC spindle, forces multiply invisibly. At 18,000 or 20,000 RPM, rolling elements in spindle bearings endure enormous dynamic loads. Even when loads remain within design limits, the repetition count is extreme. Thousands of rotations per minute translate to millions per hour. Over months of continuous operation, micro-fatigue accumulates in bearing raceways. Tool deflection introduces additional stress. Even a few microns of bending alter contact conditions. If chatter begins, vibration frequencies interact with structural resonance. Amplitudes increase. Energy transfers into the spindle housing. Bearings absorb the consequences. There may be no crash, But after a year of aggressive high-speed machining, the spindle may require revision earlier than expected. A machine designed for 5 years before major service may require overhaul in 2 or 3. A modern 5-axis machining center can cost well over 500,000 euros. In automated cells with pallet systems and tool magazines, investment climbs even higher, yet the purchase price is rarely the biggest cost. Downtime is 2 weeks without production can exceed the cost of a spindle rebuild. Delivery delays trigger contractual penalties. Customers lose confidence. Production schedules ripple across supply chains. Trucks wait. Assembly lines pause. The economic impact multiplies far beyond the original machine. Manufacturing does not collapse because of one dramatic mistake. It degrades because small inefficiencies scale silently. 5% more tool wear across thousands of parts becomes tens of thousands of euros. 3% additional scrap across months becomes millions. Slightly longer cycle times reduce annual output. Margins shrink without anyone noticing the exact moment it began. This pattern extends beyond CNC machining. Modern industry operates closer to physical limits than ever before. Aerospace, automotive, electronics all pursue higher efficiency, tighter tolerances, and faster throughput. Efficiency reduces buffer. Reduced buffer reduces tolerance for variation. The more optimized a system becomes, the less resilient it is to small deviations. Precision is easy once. Stability is hard forever. Understanding system limits matters more than chasing maximum spindle speed. Monitoring thermal behavior matters more than shaving seconds from a cycle. Adaptive feed control, vibration analysis, spindle load monitoring, structured maintenance intervals. These are not optional upgrades. They are stability strategies. The future of manufacturing will not be defined by who owns the fastest machine. It will be defined by who understands how scale transforms small variation into structural risk. Because in modern industry, failure rarely announces itself. It grows quietly, in microns and percentages, hidden inside perfectly machined parts, until scale exposes it. This is how machines really fail. Further breakdowns of industrial system failures are available on this channel.